Hey guys, welcome to my third lesson in my calculus course. And today what we're going to do is, in the last class, we talked about the properties of limits. And today what I want to do is just revise what we have studied so far. And then we'll introduce a more precise definition of a limit. And from that, we'll look at the properties of limits that I mentioned we'll need to know because these are important for differentiation and for integration later on. And then we'll go about proving these properties using this more precise definition of the limit. So definitely this lesson will be more theoretical. And so this lesson, it's good for your understanding, definitely, of the theory and to understand, at least at some level, what's going on behind the scenes, the foundations. But if you're interested only in AP calculus, or if you're only interested in AP calculus and not interested in proving theorems in calculus, then you should skip this video because I won't do any problems in this lesson. I'm just going to give you the theories and then also prove some of those theories after I revise. Okay, so there's that. The next video we'll have more of the applications. Okay, so let's go ahead and get started. I'm going to shut this off here. And so what I want to start with is just some revision and what I'm calling the informal definition of the limit. So here we have, and this is the definition that you will see in your typical calculus textbook in a university or high school. At least at some point, you'll see this definition, and you may or may not see the other definition that I will explain to you later on. So one thing here I want to point out, it says, if we have some function f, it's defined on an open interval that contains this number a, and then it says except possibly at a itself. So it means that it's possible that our function is not even defined at a, and we'll see what that looks like here in a moment. So we say that the limit of f of x as x approaches a is equal to L. Okay, so the limit is equal to this value, and we write limit as x goes to a for f of x equals L. If we can take the values of f of x, and here's the word that we're looking for, arbitrarily close to L by choosing x sufficiently close to a, but not necessarily equal to a. Okay, so what we're saying is that as our x value gets close to this a, our y value is getting close to this L, right? And we're using words like arbitrarily and like sufficiently close. And later on in this lesson, we're going to replace those words with some mathematics that will make this definition more precise. But for now, let's take a look at what exactly does that mean. And let's see, how does this work? Okay, so I'm on the very last page, right? So I want to go to this graph here, right? Okay, so now this is the exact situation that we just described. And what does that mean? Well, if you look here, we'll say that actually, we'll call this, so down here's our x-axis, and let me just make this pin so I can write with it actually. So we'll say that this point here at 1 is a. Okay, so a is this 1 down here. And so that means that here at this 2, we have our L. Okay, so we've got a and we've got L. And what's happening here is that this function, you can see there's a hole right here. And if you don't know what a hole means, it means that, not that type of, not like feeling of wholeness, but a hole. There's a hole here, meaning that if I want to know what is f of a, then we would say f of a is undefined. Okay, and this brings up a really important point about limits, is that the limit can exist despite the fact that the function is not defined at this point a. So in this case, you can see our function is x plus 1. It's simply a straight line with the y-intercept at 1. And if I wanted to know what is the limit, but actually our function is not quite the same because it is not defined at, so it's not, hold on, let me write down the definition of this function more thoroughly. So it's f of x equals x plus 1 as long as x is not equal to 1. Then you can see that reflected here. Okay, so it's a piecewise function. You can see it reflected here when x is equal to 1, we get that the function is not defined. Okay, so the function is not defined at this location. However, the limit is defined. If you imagine you are a person walking along here, as you get closer and closer to 1 here, so the limit as x goes to 1 for this function f of x, what am I getting close to? On the left side, I'm getting closer to 2. And then if I'm walking along here on the right side, I'm also getting closer to 2. So the limit as x goes to 1 of f of x is 2. But as we noted, f of 1 is undefined. Okay, so this is the first really useful idea of a limit, is that the limit can exist and give us a notion of the behavior of the function at the location where it is not defined. All right, so that's the first part here. Now let's go back and mention, let me go back like, yeah, good. So let's go back and mention the two important ideas, the left hand limit and the right hand limit. So I just want to briefly mention the notation. In order to create the left hand limit, we use this minus sign here. And it means that we're approaching from the left side of a. So for x, that will be less than a. And then we also have such thing as a right side limit. And for the right side limit, we're using this notation here with a plus. Okay, so you can use a plus on the right side limit. Now, we said that the limit can only exist if the left side limit and the right side limit are exactly the same. So if I look here at my, go back this way. So looking here at my graph, you can see that we've got a situation where the left side function is equal to the right side. I'm sorry, the left side limit is equal to the right side limit. And I can see that because as I approach from the left to right, both of these are getting closer to 2, right? So the left side limit equals the right side limit, and so therefore the limit exists. If this is not the case, then we say the limit does not exist. But if we go over here to this function, you can see that if I approach from the left side, what's happening is I'm getting closer to this point 1 here. So on the left side, I'm actually getting closer to, let's see, I'm going to use a different color. So on the left side, I'm getting closer to 1. But as I approach this 1 from the right-hand side, I'm getting closer to 2. And so here, the left side limit is not equal to the right side limit. And therefore, the limit as x approaches 1 does not exist. And again, you can see for this function, it's also not defined at x equals 1. Okay, so not only, in this case, not only does the limit not exist, but the function is also not defined here at this point. Okay, all right, so now we can move to looking at what we're going to call the precise definition of the limit. So let's go back here. So we looked at the right-hand limit, and we'll come back to infinite limits later on. Okay, so for a function f of x, we say that the limit as x goes to a for f of x is equal to L if for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the domain of f, the distance between this x minus a it's non-zero, but it's less than this number delta. And it follows that the distance between f of x and L will be less than this epsilon. Okay, so that might be a little confusing, but let's go back to the first definition. So what have we done here? We've simply replaced these words arbitrary, no, go back more. We simply replace these words arbitrarily close and sufficiently close with a mathematical analog, or with something that makes our language more precise. So, so what exactly might this look like? So let's go take a look at this. And I'll show you what we mean here. So here I've got a graph. And on the graph, I've got a function, this blue function here. And basically I've got this vertical line where x equals a highlighted so that we can see that this is the point we're interested in here. Okay. And what I've done is I've included these red dashed lines. And we've got around this location where f of a is, and let me just go over here and write this down. So at 1, this is our f of a, okay? And we've got around this, we've got what we call an epsilon interval. So this distance is epsilon. So from 1 to 1.5, so epsilon in this case is 0.5. Of course, we can move that, and that's the idea here. And this is also a distance of epsilon, right? So that means that this point is f of a plus epsilon. And then down here, I've got f of a minus epsilon. Now we're keeping these to be able to be changed. I mean, they're going to be changeable. I just have it like this now so you can see on a graph what it looks like. And so that means that down here, I've got a corresponding interval. So this is my a, and this is a distance of delta away. So this is a plus delta. And so this is a minus delta. Okay, and so what the precise definition of the limit is saying is that essentially I can move these lines closer and closer together. And I don't have lines down here, but basically I can shrink down this epsilon and I can shrink down this delta. And actually they're related, right? As I shrink down this delta, this distance that I'm calling delta, which is going to be infinitely small, right? As I'm shrinking down this distance that I'm calling delta, as it gets closer and closer to a, there will always be a corresponding epsilon that will also be able to be shrunken down until we could shrink the lines down, these epsilon intervals, until they're basically, they're practically zero. They're not quite zero, but they're practically zero. Okay, and so that's what we mean by this precise definition of the limit, that there is this delta interval around our value that we're approaching that always has a corresponding epsilon interval. And so when you see epsilon, delta, these are just, like little Greek letters. Epsilon always be greater than 0. Delta is always greater than 0. And so these are basically, you can think of them as numbers that are allowed to be infinitely small. All right. So if we go back to our graph from before, our previous graph. So let's see, where is it at? If you look at this graph, you can see that I don't have such an interval here, right? If I take my delta here and I make it infinitely small, so this is a plus delta, this is a minus delta. There's not always going to be an epsilon neighborhood, right? Because actually I will not be able to make these in the same epsilon neighborhood. F of a, which in this case doesn't actually exist, but f of a will not be able to be in any epsilon neighborhood. So what I mean is like this. So let me go back to the other graph for a moment and try to make this very clear. So let's go back here. Okay, yeah. So here, no matter what we do, if we have this, hold on, not 0. I didn't want to write down 0. So no matter what we do down here, this is my a, right? So I'm always going to have, we'll say a minus delta will be less than a, which will be less than a plus delta. And then there's always going to be the corresponding f of a minus epsilon, which will be less than f of a, which will be less than f of a plus epsilon. And so the idea really comes down to this: no matter how small I make this inequality will always exist. I'll always be able to find some epsilon so that no matter how small this delta gets, I can find a small enough epsilon to make this inequality true. Okay, but if you look on this other graph, that's not even possible because there's a limit to it. If I choose some a minus delta less than a plus delta, there's at some point you'll be able to see that our interval here will not be able to be made any smaller. So in other words, my interval that's from, let me erase my interval where I have how did I say it? F of a minus, oops, I meant to write minus, f of a minus epsilon less than f of a plus epsilon. Now I can make one of these intervals, but it will not be able to go smaller than this, right? So there's not, for every delta that I could have, there's not an epsilon. So in fact, there's no limit according to this definition. And in fact, the problem is going to be able to be useful later on. Okay, so for every delta, there does not exist an epsilon, so that as the intervals, as the inequality that we've created here, as the interval gets smaller, so the interval from a minus delta to a plus delta, as this interval gets smaller and smaller, this interval will not be able to get arbitrarily small. So as delta gets smaller, smaller. In fact, there's a limit on how small we can make delta as well, right? Because actually there's not. So yeah, we could make delta as small as we like in this case, because we're only talking about the x coordinate, right? So in fact, I can make delta infinitely small, but there's a point at which we can no longer make epsilon smaller, and that's going to be wherever, like close into here somewhere, right? And so that means that there's no limit. And that's what we mean by the precise definition of the limit. Okay. And that's what the epsilon, and hopefully that explains the epsilon and the delta and all of that as well. So now let me go back to, let's see, I've got, we're going to use those later. So we've got our precise definition of our limit. And I'm going to come back to, we have also such a thing as infinite limits. We'll come back to that. And so now what I want to do is go on to discuss the properties of limits. Okay, so as I mentioned, the properties of limits are really important to learn because they will also carry forward to derivatives and carry forward to definite integrals and integration in general. So, or at least a special kind of integration that we use in calculus. Okay, we'll stay with that. So here we've got, first of all, the constant. If c is some constant, so we're assuming it's a real number, okay, then if we take the limit as x goes to a for c, it will always be equal to c. And this is actually very easy to visualize. If I have some xy coordinate plane here, and my graph is simply a horizontal line, we'll call it c, then it doesn't matter what x I choose, you know, the y value is always c. Okay, so that's what we mean with this one. If you can just think of it as the limit of a horizontal line as you change the x value, as x approaches any value, the horizontal line only can take on one y value. So that's one way to think about that geometrically. And we can also prove this algebraically, which we will. We also have the identity, the limit as x goes to a for x is equal to a. And we'll talk more about this, but this also has to do with something called the direct substitution property. Okay, then we have the sum and difference rule. If the limits for f of x as x goes to a equals L, and the limit for g of x as x goes to a equals m, and they both exist, then we can find the sum of their limits simply by adding them together, adding the limits together. So another way to think of it is that if I have two limits, so let's say just one other way to reformulate this is that I can also write down this, which is, so this is really what the right hand is, right? I could write it down like this as well. And this is how you'll usually, this is how you'll usually see it come up, where you'll have the sum or difference. So here's g of x. Okay, so what it's saying is that I can combine these into one limit, like this. And that's going to be working for addition or subtraction. Okay, so let's see. The next one is multiplication, so products and quotients and a power. Okay, so here, these are also going to be very useful. If we have that the limit exists for both of our two functions, right, and they're both some value. In this case, I guess we're assuming that they're finite values, right? So the limit exists for this function as x approaches a, it's L, and the limit exists for g of x, it's equal to m. Then it means that we can actually multiply these two limits together. We can take their product, and the product of the limits will be the limit of the products. Okay, so the product of the limits is the limit of the products, or you can say the limit of the products is the product of the limits. Either way, up to you. We also have the quotient rule. And so this is saying that the quotient of the limits is the limit of the quotients is the quotient of the limits, provided that the bottom one is not zero, of course. And this one, the last one, is a power, which is also very useful. And this also, I know it says n is a positive integer here. This also works for rational exponents. So if you have a square root, if you wanted to take the square root of a number, you could, if you want to take the square root of the, if you want to take the limit of the square root, you can take the square root of the limit. Okay, so that's what we're saying here. If you want to take the power, take the limit of f of x to the power of some value, then it's the same thing as basically you're like putting, you can think of it as like you can put the limit inside the parenthesis, take the limit first, and then apply the exponent. Okay, so that is this one. So now let's see, I kind of want to start to set up the proof, but I think I'm going to stop. I think I'll stop this video here. In the next video, I'm going to be proving, at least starting to prove these limit properties, because in calculus and in mathematics, once you get to a certain level, we're not doing arithmetic anymore. We're not just doing calculations for trigonometry or physics. We're studying mathematics, and so therefore we also need to include the proofs of the theorems and the derivations of the formulas, so that we can at least understand and have seen what all is involved in the mathematics. Okay, so I'm going to start the next video with the proof of these properties. Okay, so that's it for this video. Hopefully that helps. Leave any comments, suggestions, or if you notice a mistake in my mathematics or in my understanding, please also mention that in the comments below. Thank you very much.